Greetings and welcome back. Last time what we did is looked at the conformation, or that is to say the rotations of bonds in three-dimensional space for alkanes. Today what we're going to be doing is looking at the three-dimensional space that tends to be occupied by cycloalkanes, or alkanes that are cyclized. Today we're going to consider only 4 cycloalkanes, and these are going to be the most common 4 that we will see throughout this class. The first is cyclopropane, and cyclopropane is the smallest possible cycloalkane. It's simply 3 CH2s made into a little cycle. Alright, in three-dimensional space it looks like this. Hopefully you can see some problems with this. This is the cyclopropane I made with my models. You can probably tell that the bonds are pretty torqued because this is all sp3. All of what we'll be doing today is sp3 hybridized carbons. They have 4 regions of electron density, and therefore they're making 4 single bonds. And so their interior angle should be 109.5 degrees. But notice that this guy, in a triangle, has an interior angle of approximately 60 degrees. And that is a bit of a disaster. So in terms of bond angles, a cyclopropane is very strained and therefore very unstable. Let's look at it from a different view. So here we see the conformation looking down this bond right here. And when we do that, we can tell that the thing is completely eclipsed. Our dihedral angle is 0 degrees. So between this guy being eclipsed and also having a really significant bond angle strain, this is a very unstable molecule. All right. So we don't see this one very much in nature, and we're just going to kind of move on. So let's look at cyclobutane. Cyclobutane, of course, is 4 carbons in a ring, and it is going to look a lot like a square. So let's see what this guy looks like. So once again, you can see that the models are a little bit messed up, and these bonds are a little torqued because the interior angles of a square are 90 degrees, which is much closer than 60 degrees to where it should be. Again, where it should be, since this is tetrahedral or sp3 hybridized, is 109.5 degrees. So we're getting closer, but we're still pretty strained. So once again, this is quite unstable. And so let's look at it kind of the Newman projection point of view. So we're looking right down one of the bonds in this molecule. In this case, what you can see is that I took this kind of squared molecule, and instead of laying it flat, I puckered it a little bit. I took this kind of top front carbon and moved it over to the left a little bit so that we don't have complete eclipsedness along this bond right here. So our dihedral angle is not exactly 0 degrees. It looks like it's kind of closer to about 5 or 10 degrees. So it's spread out a little bit kind of in three-dimensional space so that it's not completely eclipsed. That makes it a little bit more stable. However, when you pucker one of your carbons away from being flat, what it does is it decreases the interior angle. So by puckering this guy and making it a little bit more stable in terms of a dihedral angle, what we have done is we've taken those interior bond angles and made them actually a little bit smaller than 90 degrees, which is once again bad. So we don't see this one in nature very much either. I'm going to call this eclipsed question mark because it's mostly eclipsed still. But these two are disasters when it comes to stability, and so we don't see them very much. The two that we do see the most in nature, and therefore are the most stable, are cyclopentane and cyclohexane. So let's look at cyclopentane. Cyclopentane is 5 carbons, and therefore it would form a pentagon. If you remember your algebra, which I'm sure that you do, the way to calculate the interior angle of any shape is an equation that leads us to knowing that that interior bond angle is 108 degrees for a pentagon. All right, let's look at how this is for the structure. All right. These interior angles, again, are 108 degrees, which is very close to 109.5 degrees. However, you can imagine if this thing is lying completely flat, then when you look at it down one of these angles, it's still going to be completely eclipsed. So what we do is we take one of these carbons and can pucker it up. And I'll let you play with these guys in class so that you'll be able to see them a little bit better holding them in your hands instead of just two-dimensional space. So if we pucker one of those up and turn it on its side, it looks like this. So what you can see is by puckering one of these carbons off to the side, and in this case you'll see that it's this one right here that we pulled a little bit off to the left side. The other four carbons are pretty planar, is that we're able to get a relatively staggered conformation here. So we look at this dihedral angle here, it is a bit staggered. It's not completely staggered, but it's certainly not eclipsed. And therefore, a cyclopentane is a lot more stable than a cyclobutane or a cyclopropane. When we twist this guy around, we would find that of those, we can look down to these 5 bonds because there's 5 bonds in a pentagon. 4 of these 5 bonds, when you pucker one carbon, are staggered. One of them still ends up being eclipsed. So the bond of this back carbon and the back bottom carbon would still end up being eclipsed. But one of them is eclipsed, 4 of them are staggered. So that's pretty good. Furthermore, when we pucker this guy inwards, we do decrease the bond angle from 108. It becomes a little bit smaller than that, but it's still relatively close to 109.5. All right, so lastly, let's look at cyclohexane. Cyclohexane is the most common cycloalkane that we will see because cyclohexane ends up kind of fixing all of our problems. So let's look at how this goes. First off, a hexagon would have an interior bond angle, all things being equal, of 120 degrees. 120 degrees would be good for sp2, but it is a little bit higher than it should be for sp3. So this is what we would see with this molecule. And you can see that these little bonds in my model kit are actually a little torqued the other way because they should be 109.5, so it should be an angle more kind of like this, but instead they're twisted out a little bit to make it completely flat. And that makes it a little bit larger than it should be if you lay it completely flat. However, if we take a couple of these carbons, we'll take this one, and pucker them, what we can do is we can fix the problem of our dihedral angles being completely flat. Therefore, we can make it into a staggered molecule a bit, and we can take the bond angle and lower it at the same time. So let's look at this from the side. We'll pucker 2 of these up and lay it flat on its side. So this is what we call a boat conformation. What it looks like in 3-dimensional space is basically this. So we have 2 carbons, again here and here, that are puckered up, and those correspond to these 2 carbons that I've puckered up to the side. And when we do that, what happens is that the interior bond angles again get smaller, so these interior bond angles, so we'll just say this one right here, are actually going to be really close to 109.5 degrees, which is wonderful. So our bond angles in the middle are perfect. And when we look down a lot of these angles, so for instance if we looked kind of down that carbon-carbon bond right there, what we would see is that in 4 of the 6 carbon-carbon bonds we have completely staggered conformations, which is wonderful. So we fixed our interior bond angles and 4 of our 6 carbon-carbon bonds are staggered. Unfortunately, when we look down the other 2 bonds, and that would be the bond made between these 2 carbons, the 1, 2 on the left, and these 2 carbons on the right, is that they are completely eclipsed. So we've got 4 bonds that are staggered, 2 bonds that are completely eclipsed. So the boat in general is not very good. Well, what can happen if instead of just puckering both of those guys up, we pucker one of them up and one of them down? That would lead us to a new conformation that looks like this. This guy, which in 3-dimensional space is more like that, is called a chair. We call this the chair conformation. And in the chair conformation, once again, we have some carbons puckered In this case, what we've done is we've basically taken this carbon on the left and puckered it up, and this carbon on the right and puckered it down, so that the other 4 carbons, these 4 in the middle, are still basically parallel to each other. So imagine a line right here that's basically flat, and what you've done is puckered the one on the far left up and the one on the far right down. So this gives us a chair conformation. And when we look at this from the side, we can see that things are very well staggered. And as it turns out, in the chair conformation, every single dihedral angle is 60 degrees. So these guys are technically gauche, but they are definitely staggered. And as you look at these 6 carbon-carbon bonds, every single one of them ends up being staggered. So the chair is pretty much the ideal circumstance for a cyclohexane, because the interior bond angles are right around 109.5 and those dihedral angles are all staggered. All right, so the chair is great. So let's look a little more closely at the chair as it appears in 3-dimensional space. This is again kind of looking at the chair from the side. What we see is that there are 6 bonds that make up our cyclohexane. So I will draw this off to the side as a flat molecule. And we have 1 carbon that's way off to the left, which I will circle in green in both of these cases. And when we have 1 that is way off to the right, which I will circle in blue. All right, and the one on the left that's green is puckered up. The one in blue off to the right is puckered down. All right, and the other 4 carbons are all going to be parallel. So what you need to be able to do is draw this in 2-dimensional space on your page. And the way that I encourage people to do that is to look at these 2 bonds in the center. The 2 bonds in the center are always going to be parallel to each other. So the way that it's drawn right now, they're going to be going up and to the right and up and to the right, essentially in front of each other. And you can imagine an imaginary line that's kind of going like this, where those guys basically end in a parallel line. And then for our blue carbon, which is the one off to the right, it is puckered down like this. And the green carbon, which is the one off to the left, is puckered up like this. And that is how we can draw the main shape of the chair. So kind of as the chair is, the head is on the left, and in this case the feet is on the right. You could draw it the other way around, and we'll get to that a little bit more in the next video. So the other thing to notice in this case is that we have 12 hydrogens coming off of it. We have 6 hydrogens that are sticking straight up or straight down. You'll notice that we have 1 here, 1 here, and 1 here that are straight down. And then we have 1 here, 1 here, and 1 here that are straight up. What you might notice is that as you kind of count your way around this ring, 1, 2, 3, 4, 5, 6, the 3 carbons that are basically puckered down have a hydrogen sticking straight down and down over here. And the 3 carbons that are puckered up have a bond that is sticking straight up. And so we can draw those in on our structure that we have done here. So every other carbon is puckered up, and those all have a bond sticking straight up. Every other carbon is straight down, and those all have bonds that are sticking straight down. All right, those are called our axial positions. And that nomenclature comes from the fact that if you imagine this guy kind of like a sphere, we have an axis of the Earth. All right, as the Earth rotates, we have an axis that is straight up and straight down, and all 6 of those bonds, 1 on each carbon, lay in that axis. The other thing that we denote for our Earth is that we have this little plane right in the center called our equator. And we have on our molecule 6 more bonds, and I will make those dark blue. Those are all off to the side. And we call those guys equatorial. Because, and you'll see this better when we look at some of these in class so that you can actually see the molecules. That the 6 that I've drawn in yellow are straight up and down, but these guys are on a plane all off to the side. So they're all sticking in different directions but off to the side. So let's try to draw those in. So they will always be off and to the side. And so the 3 on the left are all going off to the left. The 3 on the right are all going off to the right. And what happens is that those kind of actually get spread out in space the best that you can. Notice that the way that I've drawn those, these equatorial positions are not exactly sideways. They are instead kind of at a 109.5 degree angle from the axial positions. And in fact, the 2 that are kind of on these frontmost carbons are actually sticking out at you a little bit, and the 2 in the back are actually kind of going away from you, but we don't usually draw it that way. So this is how we will always draw cyclohexane. And no matter what the substituents are, or whatever the groups are that are at the end of those bonds, and the one that I have right here, they're all hydrogens, but they'll always be attached at those possible places. So I'm going to draw this again from scratch really quickly. We're going to start with 2 parallel lines going up and to the right in the center, and I'm going to have them kind of end at an imaginary line that is straight up and down. And then remember again that we're alternating up and down. So these carbons are down, these carbons are up. And then after that would be down, so we would have one puckered down over here. These 2 carbons are puckered down, so we would need to have another one up. I'll draw that in. All right, and then I'm going to draw in my 6 axial positions. Every single carbon would have an axial position either up or down. We're going to start at this carbon at the top here. This one is up, so therefore it'd have an axial up, and then we'd have one down, up, down, up, down, all the way through. To draw in our equatorial, let's start with the 3 carbons on the right, and they would all have equatorials that are sticking off and to the right. And then the 3 on the left would have an equatorial that is off and to the left. And that is how we draw our cyclohexane. So please practice that. We'll look at these in class, and I will see you soon.